Hello guys, in this lesson we're going to be discussing colligative properties. Those will differ based on whether or not the formula is molecular or if it's ionic, so we'll take a look at that. And it has some pretty wide-ranging effects on water, including freezing point depression and boiling point elevation. The homework that we will do for this lesson is 38 to 42 on these pages. This should be the header of the classwork page that you'll make for these notes, and the aim is what are colligative properties. And there is a quiz associated with this lesson, so make sure that you've been studying the things that have been happening recently to get ready for the quiz. Okay, so colligative properties. This has to do with why we put salt on the sidewalks and roads in the winter to melt the ice. One thing you may remember is that in the presence of water, salt will dissolve. But you may have understood that salt would only dissolve in liquid water. The truth is, salt will also dissolve in solid water, but in the process, it may turn it into liquid. So I have a question for you. Why do you think people put salt in the water when boiling pasta? I've heard several answers to this before. I've heard some people say that they put salt in the water so that it boils hotter, so that it boils faster, and some people say that they just put the salt in the water to season it. What do you think? So the colligative effect deals with this idea that salt is dissolving in water and making changes to the way the water behaves. So the colligative effect's definition is here. The raising of boiling point and the lowering of freezing point compared to pure water as a result of the dissolution of any substance. This graphic will help you understand. So for pure water, we know that it freezes at 0 and boils at 100, at least for Celsius. And that gives you a space of 100 degrees during which the water is liquid. However, if you were to dissolve any substance in the water, it would freeze at a lower temperature and boil at a higher temperature, just like this graphic demonstrates. So this is a result of the colligative effect, meaning that as a result of dissolving something in the liquid, you have a lower freezing point than the original, and you have a higher boiling point than the original. Overall, it does have the effect of broadening the range of temperatures at which the substance is a liquid. It would only be a solid way down here, and it would only be a gas way up here. So when we put salt on ice in the winter, what we're doing is we're dropping the freezing point to a temperature lower than the original. And assuming that it's not super, super cold outside and you're not below this temperature, then the water would turn back into a liquid. It would be in this range and it would be liquid. And that's why we put ice on the sidewalks in the winter. Colligative effect. For instance, we have molecules at the top, which are all nonmetals. We have ionic down here in the middle, some simple binary ionic compounds. But down here, we have some ionic compounds that have, instead of just 2 atoms, we have a 3-atom ionic compound. And all of these guys will behave differently. I would start by suggesting that when you put a mole of that's sucrose in the water, it will dissolve, but it won't split up into ions, and that's because it's a molecule. So you'll just have solid sucrose, and then on the other side you'll have aqueous sucrose, but it won't have split up into more than one piece. So 1 mole of sucrose is going to yield 1 mole of dissolved sucrose. But if you were to take a binary ionic compound and dissolve it in water, you would get something called dissociation, and dissociation is when the ions separate. And during the dissociation process, perhaps you would start with a mole of sodium chloride, but after the dissolving has happened, you would get a mole of sodium as well as a mole of chloride, as those ions have dissociated. If you're keeping track, that means you now have 2 moles of ions dissolved in water compared to the 1 mole of molecules that were dissolved in water up here. And this problem can even become worse if you put a mole of an ionic compound that has 3 atoms dissolved in water. Because in that case, the 3-atom compound will dissolve into, in this case, 1 mole of calcium and 2 moles of chloride, which, if you're keeping track, is 3 moles of ions dissolved in the water. So the reason why we have to point all of this out is because the question is being asked, do all of these substances have the same colligative effect? And the answer is no. The substance that can produce the most moles of substance dissolved in water is going to have the largest colligative effect. And in this case, it's going to be calcium chloride. So at equal aqueous concentrations, which of the above solutes would have the greatest colligative effect? It would be CaCl2. And the reason why is because it's going to produce the most dissolved ions. All right, let's take a mathematical look at freezing point depression. So a freezing point is the temperature at which a liquid will change to solid. So for water, the temperature at which it would change to a solid is 0 degrees Celsius. So if you were to hold water at -2, it would be a solid. However, if you were to hold not pure water, but a water that had a 1 molar concentration of calcium chloride in it at -2, I wonder what phase that would be. Let's use this graphic to help us figure it out. So all the way down here at the bottom, you can see that if you have 1 molar calcium chloride, it won't freeze until it hits -6. But -2 is above that temperature, and that means that water won't have frozen yet, and it would still be liquid. Now, calcium chloride is a particularly strong colligative effect, but since it has 3 moles of ions in every mole of the substance. And that's the reason why we prefer it over a molecular substance or a simpler ionic substance like sodium chloride, because it breaks up into 3 moles of ions. I would also add that every mole of dissolved particles depresses the freezing point of a 1 liter solution by about 2 degrees Celsius. So that would mean that the freezing point of a 1 molar calcium chloride solution is still -6, or -2 times 3 moles is -6 degrees Celsius. Now let's talk about boiling point elevation. A boiling point is the temperature at which a liquid changes to a gas. For water, the boiling point is 100 degrees Celsius. You can see that here. Boiling point of water without sodium chloride is 100. So that means if you had water at 100.5 degrees Celsius, it would definitely turn to gas. On the other hand, if I had a 1 molar sodium chloride solution at 100.5 degrees Celsius, my argument is that it would be liquid. And my reasoning is that the boiling point of a 1 molar sodium chloride solution is 101. 101 is the point where it would turn to gas, but 100.5, of course, is lower than that, so I would argue that it would remain liquid. So let's come back to the original question of why do people add salt to pasta water so that before they make the pasta? Some people have said that it boils hotter, and we can see up here that there might be some evidence that that's true, because when you put the salt in the water, it will boil at a higher temperature, which is 101 in this case. So what you should know is that every mole of dissolved particles elevates the boiling point of a 1 liter solution by about half a degree Celsius. So the boiling point of 1 molar sodium chloride would be 2 times 0.5, which would give you 1 degree Celsius. In other words, if you put a mole of salt in water, you would get a 1 degree Celsius elevation in boiling point. So maybe people are right. Maybe they are doing it to boil hotter. But I would add one other important point. A pinch of salt, which is what you really add to the pot of water, has a mass of about 0.36 grams. But if you were to actually take a mole of salt, that would have a mass of 60 grams, or about 60 paper clips. Now, none of us add that much salt to the pasta water, and I think that's the reason that the real purpose of salting a pasta water is for seasoning. And with that, we've reached our pair-up. So please copy down these questions for your pair-up. Don't answer them. Then follow it with these questions for summary, which you also won't answer, but we'll talk about them in class tomorrow. Thanks for watching and have a good night.